Everyone, this is the second video for Baeyer Villiger oxidation. So in the first part I have already covered these three. Okay, so this is the introductory part, so I will request you to watch that video first, otherwise it will be difficult to understand these examples. So in today's video I'm going to focus on some diverse examples of Baeyer Villiger oxidation. So let's start. Here we have the first example where we will see how the stereochemistry is intact. As we know, because of the concerted mechanism we have seen in the previous video, the stereochemical integrity is maintained. So in the starting material you can see there is a chiral center. There in the right hand side also there is chiral center. But we have to focus the actual group where the oxidation will take place. So here we have a carbonyl group, right? Now this carbonyl we will not consider because this is basically amide, and because of this lone pair donation, the attacking tendency of the nucleophile towards this carbonyl carbon will not be very high. So that is why we will focus on this carbonyl carbon. Now because this group we know the migrating aptitude, this group is 3 degree, so this will be considered as the migrating group. So oxygen will be inserted between these two carbons. Fine. So this is our product. As you can see, with all the stereochemistry they are intact. The second example, here also we have this chiral center here, and if we focus on both side groups, here we have methyl group and the other side we have 3 degree alkyl group. So that is why this group will be the migrating group. So this is the migrating group RM, and oxygen will be inserted between the migrating group and the carbonyl carbon. Fine. So this is our product. One more interesting example, that is the third example, where we can see the stereochemistry is intact. Now at a first glance it seems very complicated molecule, but we just have to focus on that part where the reaction is going to take place, right? So this is the carbonyl carbon where the reaction will be occurring. This is the H star, so we will not consider it. Now there is also a CC double bond where epoxidation can take place, but because of this stereochemistry, because of this sterically hindered position of this CC double bond, mainly here reaction will be occurring at the C double bond O only. So what we will do, this group we can consider as if this is a G and it will remain intact. Now this side we have a methyl group and the other side, that group obviously will be the migrating group, right? So that is why the oxygen will be inserted at this point. This CC bond, oxygen will be inserted between this CC bond. Okay, so CH3CO, so I will just write the part of the molecule where the actual change is happening. Okay, so this side and this side there is no change happening, so as if this total part, this is our G. So here we are getting A star from this CH3CO group, right? Presence of electron withdrawing groups. In the left hand side we have here R, and in the right hand side we have a long chain. Now depending on what kind of R, we will see whether it is A or B. Now electron withdrawing group that we will have in this R part. So look at this table. When we are changing this R from methyl to CHF2, then CF3, then CF2, CF3. That means we are gradually increasing the number of fluorine electron withdrawing group. Now interesting part is, suppose when it is methyl, we will expect that this group will be the migrating group, right? That you already know. So A should be the product because oxygen is inserted between this long chain and this C double bond O, and B we should not get. But even if you are changing this CHF2 or CF3 or CF2, CF3, then also see yield of B is always 0. So yield of A, it is first 99, then 87, then 64, it is gradually changing, and it is the conversion in percentage. Now see, as we are moving, increasing the number of electron withdrawing group, this yield of A is increasing. B is not, we are not obtaining it, that is fine, but yield of A, that is also gradually decreasing. Now what is the reason behind it? Migrating group is always this part, that is fine, but still, though this group is not migrating, but it is having some effect on the overall yield, right? Now to understand it, you have to consider this tetrahedral intermediate. So this tetrahedral intermediate, remember in the last video also we have already seen this intermediate. Now in this intermediate, if this is a migrating group, but in R group actually we are gradually adding some fluorine. So this R group, when there is electron withdrawing group present, it is basically increasing the stability of this tetrahedral intermediate, and when tetrahedral intermediate is stable, then migration will be slow, and as a result overall yield will be less, and that is the reason here we are why we are getting this type of results. Next example, now here on one side we have benzene ring with arrow 2 group at 4th position, and another side we have simply phenyl ring. So obviously the group which is more donating, that will be migrating. So this is our migrating group, and that is the reason oxygen will be inserted between the CC bond, right? Here we will see that normal is written in the left hand side, abnormal is written on the right hand side. Now what it means? So these substrate, as you are seeing, they are bridged bicyclic ketones. So in this case, simply the migrating order that we have seen in the last video, that will, it may be that it will not be followed directly, right? So there will be some effect of this steric hindrance. So as I have mentioned, when that is migrating group, it is not only decided by the electron donating effect in the group, right? There is also some steric hindrance when present in the molecule, that also have some influence. So that is why here you can see this side we have CH2 and this side we have 3 degree. So obviously we will expect that the oxygen will be inserted somewhere here, and that also we are getting fine. In the second example also our expectation is oxygen will be inserted here because it is 3 degree, and that is also occurring. Now we will see 2 more examples where something abnormal is happening, that is not as per our expectations. Here we have CH2 group on this side, and here we have 3 degree. So our expectation is oxygen will be inserted here, but that is not happening because now the steric hindrance is increased surrounding the C double bond O. And then the next example also, not just in the surrounding, I will say, sometimes because of these methyl groups also you will see there will be some effect, right? Now in the second example, here we have CH2 group on this side and here we have 3 degree. So normal expectation is oxygen will be inserted here, but that is not happening because of this increased steric hindrance at this part. So these are the reasons why we are sometimes getting abnormal product from bridged bicyclic ketones. Next example, any group that will expect to stabilize a cation can be utilized to direct migration. Here in this molecule we have cyclohexane, but on one side we have SiMe3 group. So this is CH2 fine, this is also CH2, but see, these both sides, they are not exactly symmetrical, right? Now if this side is acting as the migrating group, what will happen? We know when it is migrating there is some positive charge generation. So positive charge will be generated at this carbon, and with respect to this carbocation, though it is not fully formed carbocation, but still there will be some positive, that is carbocation type of character. With respect to this carbocation, this is alpha and this is beta position, and we know when there is some beta silyl group, as you can see here, this is our carbocation and this is the vacant p orbital, and this is alpha position, then we have beta position, beta silyl group. So this type of beta silyl group, this carbon silicon bond, that actually helps in the stabilization of the carbocation, and that is why any group which can we can expect to stabilize the carbocation, that can be directing the migration. So that is why we are getting specifically this product, not the other side we are getting this cyclic ester. Reaction on to adamantanone. So this is, though it looks very complex molecule, but actually it is symmetrical. So it doesn't matter whether this side you consider or this side, both sides are actually symmetrical. So the product will be like this. You can also draw the oxygen on the other side, it doesn't matter. Fine. Reaction with diketone. So diketone means, see, 2 C double bond O present. Now in presence of paracid like R prime CO3H, let us general any paracid, attack can occur at any carbonyl carbon, because if you look carefully, surrounding environment, there is a CC double bond just beside this C double bond O. Other C double bond O, there is also adjacent CC double bond, right? Now both the pictures, as you can see, attack can occur at any carbonyl carbon. Now after that what will happen? This, just look at the left hand side. if this is migrating, that is one possibility. Another migration possibility is this side. So this side we have some acyl group, right? Similarly, on the right hand side, if you see, if this group is migrating, this is basically RC double bond O, acyl type of group. And we know there will be some carbocation type of nature that is generated. And another side is CC double bond. Now this type of acyl cation, they are very stable because of this type of resonance. So what we get after resonance? C triple bond oxygen, oxygen is positively charged, right? So this is stable because of this type of resonance, and that is why acyl group migration tendency is high. Now if acyl group is migrating, that means this group, this side, we will expect that it will migrate, and for the right hand side picture, this group will be migrating because these two are acyl. Now whatever you consider, left or right, you will always get the same product. So migration of acyl cation is preferred because of its stability, as I have shown in this by this resonance. So from both sides you will be actually getting, when this RCO group will be migrating, that means this bond will be broken and this will be the new bond formation. And if you consider the right hand side picture, this bond will be broken and this will be the new CC bond. Okay, so from both sides we are getting anhydride. So from diketone we are getting anhydride. VVO provides a route to alcohol or acid when you have started from some ketone. So here we have taken some general ketone structure, VVO reaction you are doing, you are getting ester, and after that, suppose you want to get the acid or alcohol, then you can do hydrolysis. Now that depends which one you want, acid or alcohol, depending on the group of nature of the group R and Rn. And similarly, if you take some cyclic ketones, now instead of this acid alcohol separately, what we will get? We will get, first of all, we will get lactone because it is cyclic ester unlike the previous case, and with ring expansion, this is 5-member ring because of this oxygen insertion, now it is 6-member ring. So this is lactone, and when you are doing hydrolysis, just like you have done in the previous case, now you will be getting the CO2H group and the alcohol group in the same molecule. So that is why it is hydroxy acid. And suppose you are treating it with lithium aluminum hydride, so this will be that is CO2H group that will be converted to OH. So you are getting diol. So these are the different possibilities that you can see from this general structure, cyclic ketone and acyclic ketone. Effect of electron withdrawing group in per acid. So suppose you are doing this reaction, one side you have pH, another side you have cyclohexane, and you are doing this reaction with these two types of per acid, that is separate reactions you are doing. So first you have taken CF3CO3H. So in both cases, this is our major product, that is fine. But interesting point is, and that has to be because we know the migrating tendency of cyclohexyl group, that is high. Now the interesting point is here it is 80-20, this is 90-10, 10%. Now the reason is, here we have electron withdrawing group, here we have CH3 group. And when you have CF3 group instead of CH3, it becomes more reactive. And when some reagent is more reactive, obviously the selectivity will be less. So this is the reason, though in both cases the first one is the major, but still there is some difference in the percentage of yield. Okay. Stereospecificity, regioselectivity, chemoselectivity. Now we can see everything together, right? So what will happen here? So this type of structure we have seen, one example I have shown in the last video for the chemoselectivity. So for chemoselectivity, here you can see CC double bond is present and C double bond O is also present. Now suppose we have this type of structure instead of this complex structure. Suppose I have just made it simple. So what happens? This is exo, this is endo. So under normal condition, if MCPB is present, then attacking tendency will be more from this side because that is the less hindered side. Now when there is some CH2OMe group, this type of group is present, now this side also becomes hindered and this is already hindered. So what happens? CC double bond, it remains intact and the attack takes place only on this C double bond. That means we are getting our BVO product, we are not getting epoxidation, right? So chemoselectivity, then regioselectivity. Regioselectivity already know that depends on the migrating group. So this side we have CH2 group, this side we have 3 degree. So obviously oxygen will be inserted here. So chemoselectivity done, regioselectivity done, and also the stereospecificity. Now here the stereochemistry is intact. In the next step, suppose I am doing hydrolysis. So what will happen? Then the cyclic ester, you know, that will be converted to hydroxy acid. We have just seen in the previous slide, right? So if this cyclic ester is broken, what we will get? From this side we will get CO2H, and from the other side we will get OH, and this group as it is. So here the interesting point is, see here this hydrogen CH2CO2H OH, they are all on the same side, right? And the CH2OMe, that is on the other side. So when we are doing hydrolysis, if we draw the molecule in a different way, that will be, it will look like this. So as I have said, this H, then from this side you will get CO2H, that is CH2CO2H basically. So CH2CO2H, AH and OH all are below the plane, right? And CH2OMe, that will be above the plane. So here this 5-membered ring, how we have drawn, this is our 5-membered ring, that is now planar, right? So stereospecificity, that is also maintained. So from the single reaction you can see how all these 3 we can observe. So that is why this is very interesting. So that's all for this video. Thank you for your precious time.